I'm Jared Signor, and I'll be presenting fatigue life prediction for wind turbines, a case study on loading spectra and parameter sensitivity, which is by Herbert J. Sutherland, Paul S. Veers, and Thomas D. Ashwell. For some background on wind turbines produce electrical power while also producing zero carbon emissions, so they are a welcomed alternative energy source. There are two general types of wind turbines, one being a horizontal axis wind turbine, of which the rotation of the turbine is on a horizontal axis, and the other being a vertical axis wind turbine, where the rotation of the blades is on a vertical axis. Here you can see a horizontal and a vertical axis wind turbine side by side in this short video. So what fatigue problems do wind turbines have? Well, early attempts at using a modern wind turbine faced problems, initially thought to be caused by poor aerodynamics. However, with the use of a strain gauge, it was found that the blades were loaded to almost their yield strength for every rotation. This was in the early 70s, done by Sandia National Laboratories. Another research attempt in the mid-70s of the NASA 100 kilowatt Mod Zero failed due to fatigue earlier than expected. Numerous cracks were found on visual inspection, located between a steel spar and the aluminum stress skin of the blade. The failure was due to wind shear and also an underestimating of the wind blockage done by the tower. Another example of wind turbines facing fatigue problems was in the early 80s, where nearly all wind turbines built in California experienced fatigue problems if the average wind speed was over 7 meters per second. However, inspection and maintenance of these machines have improved immensely over the years while working on them. So why do wind turbines have so many fatigue problems? This is due to the fact that they endure whatever nature throws at them. They must rotate to a variety of wind speeds, generally 12 to 60 miles per hour, and when in a park state, they must withstand extreme gusts of wind up to 120 miles per hour. A 30-year fatigue life for the wind turbine would be about 1 billion cycles, with turbines generally having 30 to 60 rotations per minute. It has also been underestimated how erratic the wind speed and direction would be. The turbines were originally tested with a relatively uniform incoming wind, with slow changes similar to how planes are tested. However, it was found that on Earth's surface, wind changes drastically in both time and space, causing extreme turbulent-induced load on the blades. Now we move on to the economic issues that wind turbines face. With wind turbines needing to endure the service lifetime of an aircraft every 3 months, it appears that very high-tech and redundant design applications could be used to solve some of these problems. However, wind turbines are intended to be used for large-scale electrical power production, and with that comes the profit margins of electric companies. Wind turbines need to be able to compete economically with other electrical power sources, most of which have already been built and in use for years. Due to this, wind turbines are typically made of fiberglass composites used in boat building, or aluminum alloys, rather than aerospace-class materials that would reduce weight and enhance reliability. So what is the problem we're looking at here? Well, it is very difficult to predict the fatigue lives of wind turbines. This is due in large part to just how erratic the wind speed and direction can be. Here is raw data taken slightly upwind from a turbine. As you can see, the wind speed is very erratic, and in just 20 seconds the wind speed fluctuates from 9.5 meters per second to 13.5 meters per second. These wind speeds are shown along with flatwise bending, which is bending about the chord line of the airfoil, and lead lag bending, which is perpendicular to the chord line. So what is the author's approach to this problem? Well, the author uses a code called Life2 to approximate the wind turbine fatigue life. Within this code, loading spectra are broken up into smaller problem sets depending on the operational state of the turbine. As well, the stresses at each nominal wind speed are defined by a histogram of stress cycles, which you can see here. Also, the annual damage at each wind speed is determined by integrating over the stress cycle distribution, weighted by the amount of time spent at that wind speed, and using Miner's rule to sum the damage based on constant amplitude SN data. The total damage is calculated by integrating over all wind speeds, and any other damage such as startup or buffering when parked are added to the annual damage rate. Due to the complexity of the varying stresses, the author introduces some assumptions that will be made when calculating the fatigue life of a wind turbine. First, the material response must be nominally elastic, due to the wind turbines experiencing a large number of cycles. The discussion will also be restricted to an SN analysis using Miner's rule, and the internal stresses on the turbine blade are assumed to be beam bending with local stress concentrations at bolt holes and other non-uniformities. Now, the author's approach to incorporating wind speed distribution is modeled using a Weibull or Rayleigh probability density function, with the Weibull function being defined by the average wind speed and a shape factor, and the Rayleigh distribution being a special case of the Weibull with a shape factor of 2. Now, in order to utilize a stress-based fatigue life approach using Miner's rule, an SN diagram is necessary. This is an issue because the available SN data typically has very little information on cycles up to 1 billion, which is what wind turbines are meant to withstand. Due to this issue, material fatigue properties were derived from extensive coupon test programs. And in this example, the author is only examining operational stresses on the turbine, neglecting start-stop cycles or stress when the turbine is parked. Here, the author uses a narrow-band Gaussian model for stress response. Now, looking at these plots, we can see the author's analytically predicted flatwise RMS stresses compared to the measured flatwise RMS stresses, obtained using a beam finite element model. As you can see, these two plots are very similar. Now, the turbine itself has been operated at fixed speeds ranging from 18 to 38 rotations per minute, as well as continuously variable speed mode, with the variable speed mode being used to find the highest aerodynamic efficiency of the turbine. So for the fatigue life estimate of the turbine, the author lays out two baseline sets of parameters. The first case uses the Rayleigh distribution with an average wind speed of 14 miles per hour, as well as the stress states obtained from the narrow-band Gaussian model with the predicted RMS versus wind speed behavior, and also incorporating this reference SN curve to determine the material properties. The second case uses measured quantities from the turbine's operating experience, the wind speed distribution from the Bushland site, the measured and adjusted RMS stress values, and the SN data obtained from the coupon tests. Now here is the reference service lifetimes for the two cases, with the top row being the analytical data used and the bottom row being the measured data used. As you can see, there's a clear difference between the two cases, with the measured values generally being magnitudes larger than the calculated values. The numbers are in years, and these are the baseline values. Now here's the life estimations comparing the three different distributions of wind speeds for the two cases, those being the Rayleigh distribution, the Amarillo airport data, and the Bushland site data. The estimations here appear to be relatively similar for the calculated case, but vary greatly in the measured case. Here, Table 4 incorporates 4 different SN estimates, and Table 5 compares the analytical RMS stress with the measured RMS stress. Overall, comparing the estimates between cases, they seem to vary in magnitude by around a factor of 10. It would be smart to take the more conservative estimates if using this data, but it just goes to show how difficult it is to predict the lifetime of a wind turbine. So in conclusion, what we've learned here is that wind turbines experience some of the harshest natural conditions and at very erratic rates. So in order to attempt to solve the fatigue life problem with wind turbines, you have to break down all elements of the problem into understandable pieces. And as the author says, this case study presented here is not perfect, but shows an approach to make sense out of the randomness of nature.